I am Professor Santosh, Assistant Professor, Department of Computer Science and Engineering. So today, let us start the discussion about the Module 2 of the Discrete Mathematical Structure, and this is the first session. So I'm just going to give a brief about what you have learned in the Module 1 and how the Module 1 information will be carried to Module 2. Fine. So in the Module 1, which was all about the fundamentals of logic. That is, you need to understand what is the logic, what is the proposition, what is the statement, and so on. And even you came up with the truth tables also. Hence, the first module has been clearly divided into two parts. The first part was all about the mathematical logic 1, what I can put it into, and the other part, mathematical logic 2. In the mathematical logic 1, you studied about the proposition and the statement along with the truth values and the truth tables and the logical connectors which we are going to make use of. And in the mathematical logic 2, we had studied we have came across the open statements, the quantifiers, and we are going to have a statement with more variables, methods of proofs and methods of disproof. So this is what exactly we have went through the Module 1. So now stepping into Module 2, which majorly we are going to focus upon the property of integers. Fine. From the Module 1, whatever the fundamental of logic we have went through, we have understood, we have been discussed. Now we are going to be in the Module 2, which is going to be a property of integers. Again, this Module 2 has been divided into two parts. The first part is going to be all about the mathematical induction. I will tell you exactly what this mathematical induction is in a few minutes. And the fundamental principles of counting. That is about the permutation, the combination, and the binomial theorem. How do I solve this using permutation or using the combinations? And even we'll discuss about how we are going to make use of the combination with the repetition. So this is what exactly we have went through the Module 1, the fundamentals of the logic, and right now we are standing at the Module 2, which is going to discuss about the property of integers. In this module, please go through this Module 2 thoroughly, because the Module 3 is again extension of the property of integers. That is where we say principle of counting part 1 is studied in the Module 2. Principle of counting part 2 will be studied in the Module 3. Hence, Module 2 and Module 3 is tightly bounded. And so please go through this concept and make sure you understand each and every step what we are going to discuss here. Hence, now let us discuss what exactly the well ordering or the mathematical induction is going to be. Let us discuss now what the mathematical induction is going to be. Fine. So now, whenever we are going to talk about a mathematical induction, fine, this word is going to be new word to you. Yes, it's a new word to me. As a discrete mathematical structure, now what is the purpose of learning a mathematical induction? Where do I use this? Do I use this in my daily life or somewhere where I can think about mathematical induction? So for this reason, I will just give you two examples, two important examples. The very first example. So just take a packet of biscuit. Fine. Just take a packet of biscuit. In the packet of biscuit, there are 10 biscuits right now. Just imagine there are 10 biscuits now. Out of this 10 biscuits, I am saying all the biscuits are sweet. All the biscuits are good taste. It's sweet and it's good taste. Fine. So now how do I prove this? So now, should I eat all the 10 biscuits? And should I say, yes, all the biscuits in the packets are sweet enough and it's tasting good? I cannot do that. And if the packet contains 1000 biscuits, or if a packet contains lakh of biscuits, every object I cannot pick, I cannot test, hence I cannot say it's proved. So it is time consuming and even it is economic consuming also. So for this reason, what exactly we are going to do is, we are going to derive some hypothesis and we will say that hypothetically I am sure that the given condition is satisfied. So for this reason, what I do is, instead of eating all the 10 biscuits of a biscuit pack and saying that all the biscuits is sweet and tastes good, what I will do is, I'm going to pick the first biscuit. I'm going to pick the first biscuit. I'm going to taste it. I'm going to say that yes, it is sweet and it is tasting good. What about the remaining 9 biscuits? Out of those 9 biscuits, randomly I'm going to pick any one biscuit now. I'm going to pick any one biscuit and I'm going to taste it. And I'm going to say that the randomly picked biscuit is also sweet and tasting good. Even without tasting, I will tell that the biscuit randomly which I have been picked is also tasting good. And now, to have an strong proof for this, that randomly picked biscuit is also tasting good, I will take the next immediate biscuit, which is just laying next to it. I'll just pick that biscuit and I'm going to taste that biscuit too. So now, I'm going to prove that the next biscuit of the random biscuit what I have been picked, if it is tasting good, and I'm going to conclude that all the 10 biscuits is sweet and this is tasting good. Now this is how the mathematical induction is going to work, and this is how we can make use of a mathematical induction. That is, I am not going to taste all the 10 biscuits, but the statement has been made that all the biscuits is sweet and tastes good. Now for this, what I am doing, I am picking the very first biscuit and I am just confirming whether the statement is good or not, and still I am not proving this. I am just picking one biscuit and I am confirming to myself that yes, it is sweet and tasting good. Next, I may pick the 5th biscuit randomly and I am going to say the 5th biscuit is sweet and tastes good. I have not tasted it, but I am putting this as a statement now. So to prove this statement, to prove this assumption what I am making for the 5th biscuit, I will pick the next biscuit is 6th biscuit now. And now this 6th biscuit, whatever I am going to pick, so now I need to prove that, it's going to be sweet and it's going to taste good. If I do this, hence I have been proved enough that all the biscuits in the pack is going to be sweet and tastes good. This is where mathematically I am inducting some theory here, and due to this theory and the proveness what I am making, hypothetically I am saying the statement what has been made has been proved and it's going to be true. And the next example what I can just make it simple is, so just imagine something like a stack or dominoes, where I have been arranged the dominoes one after the other. So now I am sure that if I am going to push the first domino, if the first domino falls, then the second domino falls, the third domino falls, the fourth domino falls, all the dominoes in the line is going to fall. So now the statement what I have made here is, I just said that all the dominoes will fall. Fine, but how do I prove this? The first domino I am going to take, I am going to see that whether the first domino will fall or not. If the first domino falls, I am going to randomly pick one more domino and I am going to say even this domino falls. And the next immediate domino, I am going to prove that as even the next domino falls. Hence, with all these 3 conditions putting together, I can mathematically, hypothetically, through induction, I am drawing a theory or statement to say that all domino will fall. Hence, the statement is proved. So this is where I bring in the mathematical induction to life, in our daily life or in the way of proving something which a statement has been made. So now, in this case, whenever I am going to talk about the mathematical induction, it is based upon the mathematical induction what I am going to have. So whatever the mathematical induction, what I want to prove or what I want to have, this is based upon the theory or on the principle of induction. It is based upon the induction principle. It is based upon the principle induction. So now this induction principle is going to depend upon the well ordering principle. So when I'm going to say well ordering principle, because again when I want to bring in this induction principle and to solve a statement and prove to mathematical induction, so this induction principle will tightly fall under well ordering principle. It's going to fall on well ordering principle. So now what is well ordering principle? So now what is well ordering principle? So we know what is order. Order is something we are going to arrange the objects in some specific order. That is what we say it as ordering. The object 1, or the element 1, the number 1, number 2, number 3 and so on. That is where we going to have the well ordering principle is going to be all about. So now this well ordering principle is going to work, and the mathematical induction whatever I am going to derive now, it is going to majorly work with the set of positive integers, which I am going to denote this as z plus. Hence, whatever the mathematical induction I am going to derive now, I am going to discuss now, or I am going to have now, it is going to be all around the set of positive integers. Hence, when I am going to have positive integers, I can clearly state what is well ordering principle. I am going to have integer 1, I am going to have integer 2 and so on. I am going to have set of integers. So now in this set of integers, whatever I am going to take, it can be the complete universe of integers or it can be subset of integers. But whatever the integers I am going to take, it should state or it should have something like the well ordering principle will say every non-empty, non-empty set, every non-empty set of integers, every non-empty set of integers. So when I say set, this becomes a subset, or I am going to say this as the subset of the universe, that is of the positive integer. So there exists a least, there exists a smallest or least element. Fine. That is, for every non-empty set or subset of Z plus, there is going to be a smallest or a least element which will help me to prove the base statement. Fine. So if this is the case, if I am going to pick 1, 2, 3, if I am going to pick the set as 1, 2, 3, 1, 2, 3, now 1 is the smallest and the least element. Hence, whichever the element you are going to take, the first element is going to be the least element, or after ordering, I need to make sure the first element is going to be the least element. So this is what the well ordering principle is going to deal about. So now, whenever I am going to have such scenarios, now this statement can also be made as, when I say well ordering, I can just put it in a simple way. So if this statement of well ordering principle is confusing, I can just say it is just a set of all positive integers, which is well ordered. Now this is what I mean. So the induction principle which I am going to use for mathematical induction is going to be based upon the well ordering principle, and well ordering principle, to put it in a simple statement, it is just set of all positive integers which is well ordered. So this is what I mean by the well ordering principle. So now if I am going to take the induction principle, the first point is make sure the set of elements from the Z plus, whatever you are going to use, it should be well ordered. It should obey the well ordering principle. If it is not in a well-ordering principle, then you cannot make use of mathematical induction to prove it hypothetically or through induct a proof to prove whether the statement is true or false. This is the first statement. You need to make sure whatever the set of integers what I am going to take, it is going to fall into well-ordering principle. So keeping this condition in mind, the next condition is whenever I am going to talk about the induction principle, what we are going to do in 3 steps. This is what we are going to do in 3 steps. The first step, when I am taking the example of a biscuit pack, I just told you my first step is I am going to pick the very first biscuit, I am going to taste it, and I am going to make sure that the statement is true for the very first biscuit, and that is where I am going to talk about verify. I am going to talk about verify, very first step. Second step, randomly I am going to pick a biscuit and I am going to assume that it will hold good for the statement what it has been made. Hence, I am not going to taste the randomly picked biscuit, but I am going to assume that I am going to assume the biscuit is tasting good. Fine. Hence, the second step is done. Now the third step, with the assumption of randomly picked biscuit is tasting good, I need to prove now that the next immediate biscuit is going to hold the statement what it has been made. Hence, I need to prove now. Hence, I am going to have verify, assume and prove. These are the 3 steps which I need to follow or I need to implement whenever I want to prove something using mathematical induction, which in turn uses induction principle, which is tightly bonded with the well-ordering principle. That is, whatever the set you are going to pick now, a set of biscuits, now it should be a set of integer. That is 1 integer, 2 integer, 3 integer, so on. 1 biscuit, 2 biscuit, 3 biscuit, 4 biscuit and so on. This is what I need to make sure the problem which I am considering now, that problem should properly fit along with the well-ordered principle. Only then think about the induction principle which is going to state or which is going to follow with the 3 steps. One is verify, assume and prove. So now this is what the mathematical induction is going to be. Now I am just going to give what is the mathematical statement is going to be all about. Fine. Now when I am going to talk about the mathematical induction, so the principle, the induction principle what I have just told you, so it is going to have some statement. The statement what the mathematical or induction principle is going to state is that, it's going to state that let the given statement, whatever it has been made, let it be S of n, because now this is an open statement, so which you had came across in the module 1. And now I am not going to discuss with you what the open statement is going to be. Fine. So I am just going to say let S of n. And for this open statement, you have been used some methods of proof and disproof already. Fine. So now this induction method is another method of proving an open statement. And for that reason, I am taking the statement as let S of n be an open statement, be an open statement, where n is a positive integer. Fine. So where you need to make sure n is a positive integer, or I can just remove this and I can just say it is positive integer. Fine. Now this is the statement, and the statement is not yet complete. The very first statement is I am just taking an open statement. Making sure that n is going to be a positive integer. Fine. So keeping this in mind, n as a positive integer, now this should hold 3 conditions. The 3 conditions what I have put here as verify, assume and prove. The very first condition is, so for S of 1, that is 1, I say the first object what I am going to pick. So for S of 1, so it should be true. It should hold true. Hence, I am going to say S of 1 I need to be is true. So it should hold true. So S of 1 is true. Hence verified. Hence the verify step is done. The second step is I am going to assume or assuming, so S of k, so where k is randomly picked value or randomly picked biscuit or randomly picked object. So assuming S of k will be true, I am going to now prove, so S of k plus 1 is true. Fine. So then prove S of k plus 1 is true, or else I can even include the statement as then. Fine. Hence, so verify the very first step, assume the second step, so prove the step 3. Now this is what the statement will go with. Fine. So if all this statement, the statement is an open statement and where it is going to work only with the positive integers, and this 3 condition holds good, hence I am going to say hence S of n is true, or I can say S of n is proved. Now this will make my complete statement starting from this point until this point. So this is where I am going to complete the statement for mathematical induction or the induction principle. Hence, whenever we are going to say what does the induction principle states, so this is what we are going to put into. So now I am just going to have verify, assume and prove. That is what I just told you. Now verify will usually happen with the very first element. Hence, I am going to verify, so making the value of n is 1, and I am going to assume for any randomly picked object. Hence, I am going to make this as n equals k, and I need to verify out the proof for the next element, so which is going to be n equals k plus 1. Hence, now my complete statement or problem, what I am going to discuss hereafter, it is going to depend upon this 3 steps. What do I follow for every statement? Hence, so make sure you understand why I am doing this or what is the purpose of doing this. Fine. So with respect to this, we'll just try to solve few problems. So using these steps and using the mathematical induction. Fine. So now the very first example, let me take a simple example, then we will just improve the complexity of the problem. Hence, the very first problem or the questions what we are going to take now is, so now I am going to make a statement that, so 3 to the power of n minus 1 is multiple of 2. Now this is the statement what I am making. Right? Now just understand. Now I cannot take for n equals 1, prove it, n equals 2, check out with, n equals 3, n equals 4, n equals 5. I cannot just go with all the integers as n until infinity or some big sets. So now I am just saying, if you take any n, so where strictly n should belong to z plus or positive integers, keeping this in mind. Fine. So now I am going to have n, which can be any integer number. Now this number should be proved that it will hold good for the statement which is going to be multiple of 2. Fine. Hence now I cannot pick every number n equals 1, n equals 10, n equals 100. I cannot do this. Hence I am going to use the mathematical induction, the 3 steps of mathematical induction to prove that the statement is holds good or statement is good. So for that purpose, the first job what you want to do is, so the statement what you have made, so you just make this as S of n, which is an open statement where, so 3 of n minus 1. Fine. This is a statement, or you can complete the statement as 3 to the power of n minus 1 is multiple of 2. Fine. And in this case, I am making a statement, the first statement. Now I need to prove that S of n is going to be true. So to prove that, the very step is need to verify. So to verify, I am going to take the first step as S of 1. The first step is S of 1. So where S of 1 is going to be 3 to the power of 1. So replace n with 1. So minus 1. So this I am going to end with. So 3 to the power of 1 is 3. 3 minus 1 is 2. And S. So 2 is multiple of 2. Hence it has been verified. So it has been verified and it is done. If it is false, then at this step I need not go for the second and the third step. Fine. I can just stop and I can say the statement is false. Now the statement is true, hence it is going to be hold good. Now I need to assume with the second step as S of k. So where I am going to assume that 3 to the power of k, because I am just replacing n with k. So 3k minus 1 will hold good is true. I am just making an assumption here. I am not testing. I am not verifying. I am not computing. I am not doing nothing here. I am just going to say this statement is going to be true. So now the next statement which I need to prove is S of k plus 1. Fine. In that case, I am going to replace n with, so k plus 1 minus 1. Now I need to prove this. If I am able to prove this, then my assumption is right. And when my assumption is right, all the statements are good enough to say the given statement is true. And for this case, I am going to have 3 minus 1. So we'll simplify and we'll try to prove this. Fine. So now in that case, I can just make this as 3 to the power of 1 into 3 to the power of k minus 1. It is just another way of writing to the power of k plus 1. Fine. So now I am going to add 3 to the power of 1. So which is just 3. And now I am going to split this as 2 plus 1 into 3 to the power of k minus 1. So I have just splitted this. I have been just splitted this as 2 plus 1. It's still same. I am just trying to simplify. And now whatever the statement I have written here. So 2 plus 3 into 3k minus 1. So let me put it over here. Now this will be written as 2 into 3k plus 1 into 3k is 3k minus 1. That is, this statement, whatever the split I have been made, I have been multiplied 2 into 3k and 1 into 3k. This is what the multiply what I have been made. So now whatever the multiply I have been made over here, now just observe here. Now this was assumed to be true. And now anything what I am going to multiply now, anything which is going to be with the multiplication of 2, now this should be multiple of 2. Fine. And now this is where I have been proved. With this case. Proved to be true. Hence, now for this case, hence S of k plus 1 will hold true. Hence S of k plus 1 is true. Hence S of n is true. That is, the statement what it has been made is going to be true now. Now this is how exactly we are going to bring in the discussion of mathematical induction. Now let us take one more example. The next example what I am going to take is the sum of n natural numbers or sum of n integers. Fine. In that case, I am going to have something, the statement what is going to stand is, so now I am going to have 1 plus 2 plus 3 plus so on until n. It is going to be equivalent to 1 by 2. If you remember the formula for sum of n integers, it should be of into n of n plus 1. So this is what the formula what I'm going to use. Fine. So now I need to prove this. Now this is the statement what I've been making. I've been making the statement as the sum of n natural number is of into n plus 1. Now I need to prove this. How do I prove this? Now should I take the value of n for every number starting from 1 to n, or I can going to use the mathematical induction. The very first step is I am going to put this as an open statement s of n colon, and I am going to say 1 plus 2 plus 3 plus so on plus n is equivalent to of n plus 1. Fine. Now this is the open statement, and the very first step or the first condition I need to verify for S1. Hence, so verify for S1. Hence, so S of 1 now is going to be, if I take 1, I should take only one element now. Hence, so 1 equals, the value of n will be replaced with 1, and this is replaced with 1. Hence, now this is going to be 1 into anything is the same. Hence, I am going to take this as 1 by 2 into 1 multiplied with 1 plus 1. And if I am going to solve this, I am going to have 1 plus 1 is 2, and 2 into 1 is 2, and 2 into 1 by 2 is going to be 1. Hence, now this is true. So 1 equals 1. It is true. Hence, it has been verified to be true. Now, I need to assume for S of k. Now, what the S of k is going to be? So, S of k will stand as 1 plus 2 plus 3 plus so on plus k equals 1 by 2 k into k plus 1. And I am assuming this to be true. Assuming this to be true, I'll go to the next step now. So where I need to prove it for S of k plus 1. So S of k plus 1 is going to stand as 1 plus 2 plus 3 plus so on plus k. Along with the k, now I need to add one more element, which is going to be plus k plus 1. This is equivalent to, because I am adding k plus 1 at the left hand side, even I need to add k plus 1 at the right hand side. Hence, for that reason, I am going to have 1 by 2 k of k plus 1 into, or sorry, it's not into, it is plus of k plus 1. Now this is what exactly you are going to do with. So 1 by 2 k of k plus 1 plus k by 2. So this is what the statement what I am going to make. Now I need to simplify and I need to prove this now. So to simplify this, I am going to take the common term, so which is going to be k plus 1. So take the common term k plus 1 and multiply this with 1 by 2 into k plus 1. That is, I have taken the common factor as k plus 1. I am just going to have 1 by 2 k plus 1. So now just to simplify further, so k plus 1 multiply this with, so just I need to cross multiply this, and I am going to have this as k plus 2 whole divided by 2. Fine. Now this is the statement what I am going to have. Now everything is going to have common factor now. Hence I am going to take this as 1 by 2. And this is going to be k plus 1, and this is going to be now k plus 2. Hence this is proved now. So just to simplify and make your job easier, let me take this as one more step. That is 1 by 2 of k plus 1. I can rearrange and write this as, I'll just open an angular bracket, and so this is going to be k plus 1 for me, and plus 1. I split it 2 as 1 and 1. And now this is going to be the statement. Now just observe here. So now I'm just going to have, for k, it is 1 by 2 k of k plus 1. I have been replaced k with k plus 1 and k again with k plus 1. And so this has been proved. Hence, proved to be true, is true, hence, so S of n is true. So this is what mathematically I am proving. The statement what has been made, as 1 plus 2 plus 3, that is sum of n natural number, is going to be true. This is what exactly we are going to do with this mathematical induction. Now this is what I wanted you to understand, or make you understand how exactly the mathematical induction will be used in the real world, or for any sort of example where the problem is going to be based upon the well ordering. And so the few example problems which have been just solved, the two basic problems, I am going to discuss more problems with respect to mathematical induction and the three major steps what I follow to prove this hypothetically. But before you meet me at the next session, I want you to solve on these problems. So please make sure you solve on these three problems. Give a try, and in the next session I will help you out to solve these three problems. But in the meantime, so please give a try. Thank you.